It's like a mirror.
Oh,
What's up, geometry students? Let's talk about playing games where when something happens, the probability will change. It's called conditional probability, where we're talking about dependent things like, hey, based on what happened the first time we played this game, the probability the second time we play it and the third could change. So um, it's all about understanding whether or not what our first action does changes our second action, or if it just starts repeating. So just pay attention to the details. You could use tree diagrams. I don't for these. I think it's more of just like understanding multiple events we multiply. So 3 cards are drawn at random from a pack of playing cards. Each card is not replaced. So that means you pull out a card. Bam. If I put that card on the side and I know that it is a face card, well, I've already grabbed one of the many face cards out of my pack. I'll have one less card in my pack. I'll have one less face card in my pack. So all of a sudden, the probability for the second draw is going to be different than the probability for the first draw. Uh, and this is very much the idea of like counting cards in Vegas for blackjack. You can see how many good cards have been played and how many good cards haven't for your future hands. So you kind of recalculate the probability of future blackjacks or future good hands. Face cards are jacks, queens, kings. So those are 12 out of the 52 cards. It's the probability that I'm going to pull a face card. But then if I've pulled one face card, I'll have 11 face cards left out of 51. And then I'll have 10 out of 50. That'd be the probability of pulling 3 face cards in a row. If it was just 2 face cards, it'd be 12 out of 52, and then 11 out of 51. Cool. Now, if the card goes back in, then every single time you pull a card, your probability of pulling a face card is 12 out of 52. That would be repeated 3 times. So understanding things can change based on the game you're playing. When you play blackjack in the casino, the cards go into a discard pile. They don't get reshuffled back into your hand all the time. So it is a conditional probability situation. What is the probability that 2 faulty pens are chosen? Well, since the boy and the girl need to take a pen, what's really confusing for students to understand with probability is like, are they doing it one at a time or at the same time? And the easiest way to explain the answer is like pretend if things are happening at the same time, like if you're rolling 6 dice at once, it's probably easier to pretend you're rolling one at a time instead of all at once. It's not going to change. Like if I'm rolling 6 dice, those are 6 independent probabilities. If I'm pulling pens out of a pen case, um, they are going to be dependent situations where the boy has a 5 out of 12 chance to pull a faulty 10. If the boy gets the faulty pen, then the girl has 4 faulty pens to choose from out of the 11 remaining. What's the probability that at least one faulty pen is chosen? This is a tricky question because it's probably better to understand the probability of working pens and if they're both working pens, then we can subtract it from 1. This might be helpful if we did a tree diagram. So the probability of a working pen is 7 out of 12 times 6 out of 11. And I'm going to subtract that out of 1. And I'll show you a different way to get this answer if you use the tree diagram. So, oops. 7/12 times 6/11, and then 1 minus that. It's a 68% chance. Um, or let's say we got the boy who gets a working and a non and a faulty. Okay, so the boy has a 7 out of 12, 7 out of 12, and a 5 out of 12. And then the girl would have 6 out of 11, 5 out of 11. And the boy or the girl gets the working pen. So that's 7 out of 11. And this faulty would be 4 out of 11. Okay. Um, at least one faulty pen chosen would be this guy and that guy and that guy. So it's the probability that we have a faulty pen plus the probability that we have a working and faulty. So that's the 5/12ths plus a 5/11ths, which if I calculate, I will find is the same as this. Uh, But no, it's not the 5/12ths plus the 5/11ths. It's 7/12ths of 5/11ths. Okay, so cool. So it's this number plus the 5/12ths. There we go. So two different ways to get the same answer. Whether you are using all of these probabilities and adding them up, or if you find just this probability and we say, oh, well, if this probability is 31.8%, then the remaining is going to be the rest. So subtract that from 100. Oh, we find those really quickly. Should probably put the decimals in there. And then you can see two faulty patents are chosen would be this 15%. And this would be this plus this plus this, or 100 minus that. Exactly one faulty pen is chosen. What is the probability that the girl chooses it? It doesn't matter if it's the boy or the girl. There's it's a boy, then a girl. Okay. I mean, I think it's a 50% chance. Is it 50% chance? If one faulty pen was chosen, we got this many and this many. So that's 26.5 times 2, or 53% of the time. But the girl chose it half of the time because like she chose it 26.5%. The boy chose it 26.5 the time, if one faulty. So 50%. I don't know if that's correct or not, but if exactly one faulty pen was chosen. Go. Bag has 4 red, 3 green, 2 yellow. A ball is chosen at random and not replaced. So because we take one out, the game changes, the probability changes. So we have to change the probability. Find the probability that both the balls are green. Well, we have a 3 out of a 9 chance on the first one. I've removed a green one, so I would have to have a 2 out of 8 chance for the one. The balls are the same color. Ooh. Well, you have the red possibility. You have the green possibility.
Yeah, I'm so
Red.
Well, we take that color and like it's your color now.
Red,
Go look
Red.
and see.
green, yellow, yellow. Those are the possibilities. If you think about this as a tree, it's like red, green, yellow. But then you have red, green, yellow, red, green, yellow, red, green, yellow. You'd have the red, the green, the yellow, adding those three probabilities up. So we could use a tree to kind of understand things, but it's probably best to just like kind of figure that out. Neither ball is red. So that would be the 5 non-red and green. And then the 4 remaining non-red green or yellow balls. At least one ball is yellow. Well, I have the probabilities that we have these guys. So that's all of the drew yellow first possibilities. But then I also have the green than yellow, and I also have the red than yellow. So I need those 1, 2, 3, 4, 5 possibilities to be added up together. And if I do it correctly, it's not going to be over 100%. So we got my 3 of these added up will just be the probability that we get a yellow. So that's 2 out of 9. This is just we get a yellow first. If we get a green then a yellow, it's 3/9 then 2/8. If we get a red then a yellow, it's 4/9 and then 2/8. Add those probabilities up here, and then those 3, which will equal that. We get our answer. %41.6%. %27.7%. Red, green, yellow. 27.7%. Okay, one of those. President had 10 members, 6 of which are girls, 4 are boys. One of the members. Okay. President is a boy. Well, 4 out of 10. Well, we have 6 out of 10, and then we have 4 out of 9. What if would be like girl first and boy first? Or 4 out of 10, 6 out of 9, right? Do we have to add those from here? These two things are the same. So first or second actually doesn't matter because it's going to be the same numbers. I don't have to worry about adding the two. Or do I? Let's think about this. Girl, boy. Girl, boy. Girl, boy. Girl, 6'10". Boy, 4/9. Girl, girl, 5/9. 4/9. Girl, boy. Boy, girl, 4/10. 6/9. Boy, boy, 4/10. Boy, boy, 4/10. 3/9. Girl, then boy chosen. Boy, then girl chosen. This is 6/10 times 4/9. So yeah, you have both. 4/10 times 6/9. I have two of these. Very interesting. Good question. So six tenths times 4/9. 4/10 times 6/9 is going to be the same. And I get 26% twice. So like doubling this. It's 53%. So that probability, which you multiply to get. No one is. Rabbits are female just by looking at it. It's crazy. All right, cool. 42 are female, 23 are female not eating carrots. That means there's going to be 19 that are female and eating carrots. Subtracting 19 from 34 is 15. There's a probability that a rabbit. Very cool. This makes sense. There's a total of 70. No. So the neithers. 23 plus 19 plus 15. 57. So there's 13 that are neither female nor eating carrots. What's the probability that a rabbit is a male? And not eating carrots. I'm just talking about females and eating carrots. All right. 42 of the rabbits are female. That means 28 are going to be male. Eating carrots, not eating carrots. Eating carrots, not eating carrots. We could Venn diagram this, two-way table this too. 23 are female and not eating carrots. Female and not eating carrots are 23. But the total, okay, so 23 of the 42, 23 are female and not eating carrots. So that means 19 are female eating carrots, which is what we found. Cool. We found 34 not eating carrots. Well, 23 are female not eating carrots. So that means 11 has to be male and not eating carrots, which means 17 have to be male and eating carrots. These should add up to be 70. So it's like male, female, eating, not eating. We have 70 total rabbits. We got 42 that are female, which means 28 are male. Cool. This is how we're working on this. Female not eating carrots are 23. This is like the easiest. The Venn diagram, this is easier. Figuring it out using the two-way table. Which means 19 here. 34 not eating carrots, which means eating carrots 66. It's crazy. We got to get to 70, not 100. $36. Okay, eating carrots, 19 and 17. Yeah. It's eating carrots. This has got to be 9, 11. Yeah, there you go. Woo! This is not. I disagree. Two-way table. Two-way table. Or tree diagram. What's the probability that a rabbit is male and not eating carrots? Male, not eating carrots is 11 out of 70. It's probability that a rabbit is female, given that it's eating carrots. Eating carrots 36, female is the 19 out of 36. Which is more likely the probability that a rabbit is male. The males are 28 out of 70. Probability a rabbit is male given they are eating carrots. They're eating carrots, 17 out of 36 is the eating carrots given they're male. Right. Given they are eating carrots, they are male. This is the winner. This is bigger. This is closer to 50%. Yes, I think it is. Yeah. 47 versus 40. All right, that was easy. The Venn diagram, I did not like. This did not help me find the males and stuff. So, like, two-way table or the tree. This is just review too. This is not conditional probability. So, probability that this customer has purchased a car with an automatic transmission. Cool. We got a three-way, 2x3. Oh, we gotta do some addition here. 64 and 16 is 70, 80. 54 and 8 is 62. 36 and 22 is 58. 16, 8 and 22, that's 30, 46. This is 154. Do these numbers add up? So annoying. Why do we have to get these big numbers? Two hundred. 200. 200. 200 cars. What's the probability that this customer has purchased a car with an automatic transmission? 154 out of the 200. Given that the customer purchased a four-door car, probability that is automatic. That's the 54 out of the 62. Two-way tables are great for these questions. The given questions, the two-way tables are great. Given that a customer purchased a manual transmission car, okay, so that's the 46 total manual transmission cars. Probability that it's a hatchback. That's the 22 out of the 46. Probability that this customer has purchased a car with an automatic transmission and a hatchback. Automatic and a hatchback is 36 out of the total of 200. Probability that the customer purchased a hatchback, a two-door, or a four-door. Don't add up the columns because you might double count things. Here's the hatchbacks. Here's a two-door. No. Here's a four-door. 100%. Cool. All right. Fun. Good lesson. Tough stuff. Tricky things. Conditional probability, and then some review questions. Good questions though. All right. Peace.